Hi, this is Tzvi Rosen with another lecture on matrix theory. In this week's class, we'll talk about eigenvalues and eigenvectors. So, as a jumping off point, we'll remember one of the geometric operations we discussed in the last lecture. We talked about, for instance, in R2, there's an operation called dilation and similarly contraction. So, for instance, if k is between 0 and 1, and we have a matrix operation which takes any vector v in R2 and returns just the same vector but scaled by k. So this is called a contraction by k. So this is for any v in R2. Then we're basically talking about this is R2, and we have, let's say, v as an input, and then our output will be red. That'll be TV. So what's trying to be communicated here is that it's just a scaled version of v. It's just slightly smaller, okay? This is called contraction. Okay. And if we have k greater than 1, then we also take our transformation to be TV equals kv for any v in R2. So this time around, let's see how much we can see how tightly we can constrain this. So we're going to take very small eraser. Great. And now we're going to take different color. Let's make it pink this time. And now TV extends our vector. So this is called a dilation. Okay? And it's not just the vector v that we drew, but any vector that you take, the way that you apply t to the vector, the way that you apply this matrix transformation is just by multiplying that vector, multiplying all of the coordinates by the same scalar k. Okay. So, but you'll also remember that we did a different kind of operation too, which only changed one of, it's scaled, but it only scaled in one direction. So for instance, if we had vectors in R2 again, so this would take something like, so if we have our standard basis vector E1 and our other standard basis vector E2, then, let's give E2 a different color. Okay. Then what this would go to in the next iteration, so after applying t, you would have the red vector staying the same. So this is the same. E2 is equal to t of E2. Okay. On the other hand, E1 gets stretched. Let's make this a little longer. Okay, so this is t of E1. Okay, and it's stretched by some factor k. Okay, so clearly we're looking at a very different region. So we're looking at a very different output than the input. For instance, this rectangle turns into this rectangle. But you might be a little bit confused. You could say, so I know how this acts on the standard basis vector in the x direction. It scales it. and I know how it acts on the standard basis vector in the y direction. It keeps it the same. But how does it act on vectors that are neither of those? What about a vector like, let's take this vector. How do we interpret what happens to that? Well, what we do is we break this down into its basis components. So we have a component in the x direction, and we have a component in the y direction. Okay, and this vector, let's call this v, is equal to vy plus vx. Now, the vx part, you scale just like e1, because it's a multiple of the e1 vector. On the other hand, vy stays the same. So what happens over here would be, this would be v equals k times vx plus nothing plus 1 times vy. Okay? So what's going on here is this scales one basis vector up, and leaves the other the same. And to get the other vectors, for other values, apply linearity. Okay? Basically, you can break it down into the two basis vectors, and then remember how your transformation t acts on each of those basis vectors, and then just act on it linearly. So, i.e., t of ae1 plus be2 is equal to at of e1 plus bt of e2. So all we really need to know is how it acts on e1 and e2. Okay, so we've now looked at dilations and contractions and matrices designed to compress or expand in a specific direction. But what if we're just given a random matrix and we want to know maybe there's some direction where the matrix acts like a compression or expansion, okay? And just scales that single vector. Is there a vector v and a scalar lambda? You know, let's exchange this v for an x. And a scalar lambda such that ax is equal to lambda x. Okay? And lambda is a Greek letter, in case you've never seen it before. Okay, so if such a vector exists, such a vector, or maybe multiple vectors, they would be really convenient to use as a basis. They would be convenient as a basis for the action of y. For the action of a. Okay? Because all you would have to do to understand what a does to any vector, so av would be equal to a times a1, e1 plus, etc. up to an, en. But if these e1 through ens, let's make this x1 through xn actually. If these x1 and x through xn are special vectors where a just scales it, this might be the same as a1 lambda 1 x1 plus up to an lambda n xn. So that by spelling out our vectors in terms of these special x's, we can just allow A to act by scaling. Okay, that's the idea. Okay, and this is what an eigenvalue and an eigenvector are. So eigen is from the German. This means its own or something essential to it. Okay, and the idea is that a matrix has eigenvalues and eigenvectors, special values and vectors associated to it. Matrix A, so it has to be a square matrix. So if V, or we'll use X. If X is a vector in Rn, and lambda is a real number satisfying Ax equals lambda times X, then we call lambda an eigenvalue, and X its associated eigenvector, or an associated eigenvector. Or is an eigenvector corresponding to lambda. Okay, let's see an example of this at work. Okay, so we have a matrix A equals 3, 1, minus 1, 1, and I'm going to claim that lambda equals 2 is an eigenvalue, and the vector x equals 1 minus 1 is an eigenvector. Okay, and how can we check that this is true? By checking the defining equation. Ax equals lambda x. Well, this would mean 3, 1, minus 1, 1 times the eigenvector 1 minus 1 should be equal to, and I'll leave it as a question mark because we're still checking it, 2 times 1 minus 1. Okay, well, let's do the matrix multiplication on the left-hand side. This is LHS stands for left-hand side. So 3 times 1 plus 1 times minus 1 equals minus 2. And minus 1 times 1 plus 1 times minus 1 is also equal to so the first one, is positive 2, and the second one is minus 2. We have minus 1 times 1 plus 1 times minus 1. This is equal to 2 minus 2. And then on the right-hand side, we have 2 minus 2. Okay. This computation allowed us to verify that a certain pair of value and vector is an eigenvalue and eigenvector. But the question is, how do you find these to start with? How can I tell, just looking at a matrix, what vectors it scales and by how much? That brings us to the characteristic equation. And the idea is as follows. We have this equation Ax equals lambda times x. And this is a matrix equation. And another way of writing this would be Ax equals lambda times the identity matrix times x. Okay, because x is equal to the identity times x. Okay, well, this is an n by n matrix, and this is an n by n matrix. So what we're going to do is combine them. Okay, we can rewrite this equation as Ax minus lambda Ix equals 0. Or equivalently, A minus lambda I times x equals 0. Okay, now this again is an n by n matrix. Okay, this is our vector. Okay, we're assuming this is not equal to 0 because obviously the 0 vector, any matrix just gives you the 0 vector back. So we have a non-zero vector multiplied by an n by n matrix, and it gives us the 0 vector. That means that this matrix has nullity greater than 0. So the nullity of A minus lambda I is at least 1. Okay. And that means a bunch of things. There are a lot of equivalent things that to the statement that a certain matrix has nullity or has a non-trivial null space. But one of the equivalent ways to say that, this is true if and only if the determinant of the matrix A minus lambda I is equal to 0. Okay? And what we have in this final equation, this is a polynomial in lambda, okay, where lambda is our variable in this equation, and it's polynomial of degree n, where n is the dimension of the matrix. And by solving the polynomial in lambda, we'll find all possible eigenvalues of the matrix. Okay, let's see this in action. And by the way, this is called the characteristic equation of A. Okay, sometimes the characteristic polynomial. Okay, let's see it at work for a 2 by 2 matrix. So we have this matrix A, and we're going to be looking at the determinant of A minus lambda times I equals 0. So again, I is, because we're looking at a 2 by 2 matrix, I is going to be equal to the 2 by 2 identity matrix. Okay, so we're looking at the determinant of 1, 2, 5, 4 minus lambda, 0 is on the off diagonal, equals 0. Let's combine that. Determinant of 1 minus lambda, 2, 5, 4 minus lambda. Okay, and this is equal to 0. Multiplying out, so the determinant of a 2 by 2 matrix is top left times bottom right minus top right times bottom left. So we have 1 minus lambda times 4 minus lambda minus 2 times 5. So we have 4 minus 4 lambda minus 1 lambda is 5 lambda plus lambda squared minus 10. Okay, and assembling this a little bit more nicely, we have lambda squared minus 5 lambda minus 6, and we know that's supposed to be equal to 0. Well, this equation can be factored. This is lambda minus 6 times lambda plus 1. Okay, so what that tells us is that the possible eigenvalues for this matrix are 6 and negative 1. So the possible eigenvalues, let's give ourselves a bit more room. are 6 and negative 1. Okay? So any eigenvalues satisfying the characteristic equation with this matrix, the only options are 6 and negative 1, because that's the only place where this polynomial has a root. This polynomial evaluates to 0. Now let's look at a 3×3 example. So here we have our matrix A, and we want to see under what conditions the determinant of A minus lambda I is equal to 0. Okay, so again, we just write out A minus lambda I. Okay, in this case, I is the 3×3 identity matrix, so we're looking at 1 minus lambda, 2, 1, 6 minus 1 minus lambda, 0, minus 1 minus 2 minus 1 minus lambda. Okay, and this is our determinant. We'll use the lines on the side to indicate determinant. We're setting this equal to 0. Okay, so we have to compute the determinant and see what values of lambda give 0 to find what the potential eigenvalues are. So we're going to expand on the third column because we have a nice 0 there and a 1, so it's relatively easier to use. So we're going to take that this is equal to 1 times 6 minus 2 minus 1 minus lambda minus 1, and add that to minus 1 minus lambda times the cofactor, which is 1 minus lambda minus 1 minus lambda to 6. Okay, and what we get is, for the first one, we have minus 12 minus negative 1 times negative 1 minus lambda. So minus, the negative of that is just lambda plus 1. Okay, and over here we have negative 1 minus lambda times 1 minus lambda times negative 1 minus lambda gives us lambda squared, and then the plus lambda minus lambda cancels, and we're left with minus 1. And we subtract from that 2 times 6, which is 12. Simplifying further, we have negative 13 minus lambda plus, now I'm just going to multiply, this is lambda squared minus 13, but I'm going to multiply through the minus 1 minus lambda. We'll get minus lambda cubed, okay, minus lambda squared. Then the minus 13 gets multiplied by minus lambda to make plus 13 lambda plus 13, okay, and simplifying, we get that this 13 cancels with this minus 13, and we're left with minus lambda cubed minus lambda squared plus 12 lambda. Or, put it a bit simpler, we have, first let's factor out the lambda, and you know what, let's factor out the minus lambda, and this is lambda squared plus lambda minus 12. Okay, and then that last quadratic factors as lambda plus 4, lambda minus 3. So we have minus lambda times lambda plus 4 times lambda minus 3. Okay, and that tells us that our possible eigenvalues are exactly 0, 3, and -4. Okay, because that's where this product of terms vanishes. Okay. Now let's look at upper triangular matrices and see how this eigenvalue conversation translates to that setting. So recall, upper triangular matrices are matrices where you have non-zero values perhaps along the diagonal and above the diagonal. Okay, all sorts of non-zeros. And then everything below here is just 0. So this is non-zero. I mean, you could have zeros there, but not necessarily, and this is 0. Okay. So that's our upper triangular matrices. In particular, Aij is equal to 0 if I is greater than j. Right? If the row that you're on is higher than the column that you're on. Okay? So this is upper triangular. And in the conversation about the determinant, so if we're looking at determinant of a minus lambda I, so that, in this case, that'll look like a11 minus lambda, a22 minus lambda, etc., down to ann minus lambda. Okay, just subtracting the lambda from the diagonal. And then a bunch of other stuff up here. But then everything down here is zeros. And one thing we know about upper triangular matrices is the determinant is just equal to the product of the diagonal. Okay. So the determinant equals the product of diagonal elements Okay, and what that means in terms of the eigenvalues is that the diagonal elements are exactly the eigenvalues. Implies the possible eigenvalues are just a11 up to ann. Okay? So let's see what that looks like in a specific example. So here's a 4x4 upper triangular matrix, and I could start, subtracting lambda and then doing a big multiplication, but we know that the possible eigenvalues here are just the diagonal elements. So these are 1, 5, 8, and 10. Okay, pretty simple. So we've done a lot of talking about eigenvalues and how to compute eigenvalues using this characteristic equation, determinant of a minus lambda I equals 0. But we've left to the side the question of eigenvectors. What vectors do we multiply the matrix by so that we're scaling by this eigenvalue, this lambda? Okay, so let's go back to the equation. So if a minus lambda I times x equals 0, this means that x is a vector in the null space of a minus lambda I. So finding vectors in the eigenspace corresponding to lambda, which is the set of solutions to this equation, is just the same as finding vectors in a null space. Okay? So the eigenspace corresponding to lambda is equal to the set of vectors satisfying ax equals lambda x, and this equals the null space of the matrix A minus lambda I. Okay. And so because it's a null space, we can compute it the same way we compute null spaces in general. Same way as a null space. As typical null space. Okay, let's see an example. So let's say we have this 2 by 2 matrix, 3, 2, 1, 2. Okay, I don't think we've seen this one before, so we have to find the eigenvectors, eigenvalues first. Step 1, find eigenvalues. Okay, and that's simple enough. You plug into the equation determinant of A minus lambda I. In our case, that's 3 minus lambda, 2 minus lambda, 2, 1. This is equal to 6 minus 5 lambda plus lambda squared minus 2, which is equal to lambda squared minus 5 lambda plus 4. We're setting this equal to 0, and that means that lambda must be equal to minus 1 or minus 4. Sorry, positive 1 or positive 4. Because this factorizes as lambda minus 4, lambda minus 1. Okay. So that's step 1. So step 2, once we have our eigenvalues, is to find the corresponding eigenspaces. Okay, so find the corresponding eigenspaces. So we'll start with lambda equals 1. Okay, so we write down A minus lambda I is equal to the matrix 2, 2, 1, 1. Okay, and now to find the eigenspace corresponding to this eigenvalue, I find the null space of this matrix. Okay, and finding the null space of this is equivalent to finding the solutions to this equation, 2, 2, 1, 1, x, y equals 0, 0. But you can quickly see that both the first and the second rows basically say that x plus y equals 0. And so that's really the only restriction. So any vector of this form will look like, this will basically look like x and minus x, which means that, so is in the null space. And in particular, a basis for the eigenspace, so a basis for the eigenspace would be just the vector 1 minus 1, okay, because scaling that vector gives you anything of the form x minus x, okay? And if you plug 1 minus 1 into this, so multiplying 1 minus 1 here, we get 3 times 1 minus 2 equals 1, and 1 times 1 minus 2 equals minus 1. So indeed, this has lambda equals 1, because when you plug in a specific vector, you get the same vector back. It gets scaled by 1. Okay, let's find the vector corresponding to the other eigenvalue. So we have other eigenvalue is lambda equals 4. And for this lambda, we have A minus lambda I equals 3 minus 4 is negative 1, 2, 1 minus 2. Okay, so we want to find the null space of this. And to do that, again, this is just minus 1, 2, 1 minus 2 times x, y equals 0, 0. So both of these equations translate into x minus 2y equals 0, or x equals 2y. So these are all vectors of the form x 2x, which we could also have generated using the basis for the eigenspace to 1. Okay, and this is going to be the eigenspace corresponding to lambda equals 4. And let's plug this in just to check that when I multiply by the vector 2, 1, I get scaled by 4. 3 times 2 is 6, plus 2 times 1 is 8. And 1 times 2 plus 2 times 1 is 4. Indeed, this matrix multiplication scales me up by 4. Okay? So in summary, we have, for our matrix A, we have eigenvalues and eigenspaces given by 1 and 4, and the corresponding to 1 is the line spanned by, is the span of the vector 1 minus 1. And the eigenspace corresponding to 4 is the span of the vector 2, 1. Okay? Now let's see some more familiar examples looking for what is the eigenspace. So when we spoke about dilation, that's where you grow every vector in the vector space by the same factor 2. And that would be expressed by this matrix, which is just 2 times the identity matrix. Well, what would we get if we tried to apply our eigenvalue techniques here? Well, obviously, if we do 2 minus lambda, so computing a determinant, 2 minus lambda, 0, 0, 2 minus lambda, this is just equal to 2 minus lambda squared, which means that lambda is the only, lambda equals 2 is the only eigenvalue. Which makes sense because you're scaling every vector by 2, so why would we find a different constant that we're scaling by? When we plug in a minus lambda I, that's equal to the complete 0 matrix, which means that the null space of this is all vectors in R2. Okay, so that means that the eigenspace corresponding to 2 is the full space R2. Okay, which makes sense again because every vector in your space gets scaled by 2. Okay, so from the first example and second example you saw, you had 2 really nice eigenvectors for a 2 by 2 matrix. But that's not always the case. Sometimes, even though you have a nice 2 by 2 matrix, you're only going to get a single eigenvector, and you won't have a collection of eigenvectors that span your space. So here's an example of that. If this is our matrix A, and we're taking the determinant of A minus lambda I, we get 1 minus lambda 0, 1, 1 minus lambda, which comes out to 1 minus lambda squared, minus 0 times 1 is just 0. So that means that lambda equals 1 is the only eigenvalue. Okay, how about eigenvector? Well, let's look at the matrix A minus lambda I. This is the matrix given by 0, 1, 0, 0, and the null space of this is the span of a single vector. 0, 1. Okay? So even though we have a 2 by 2 matrix, we find only one eigenvalue, and that eigenvalue has only one associated eigenvector. Okay? We saw before an upper triangular matrix and how it has how all of its eigenvalues are on the diagonal. That make it seem very simple, but then when you're actually trying to compute the eigenspaces, it gets a bit more complicated. So let's find eigenspaces for each eigenvalue. So starting with lambda equals 1, we have the matrix A minus lambda I is equal to 0, 2, 3, 4, 0, 4, 6, 7, 0, 0, 7, 9, 0, 0, 0, 9. Okay, and this is, we get this matrix just by subtracting 1 from every element on the diagonal. Okay, and we know that we're looking for x1, x2, x3, and x4 that send this to 0. Okay, so we can do, we can start by solving for x4 and then solve our way back. So because we have 9x4 equals 0, this means that 7x3, so certainly x4 equals 0. And then plugging that back into the previous equation, that means that x3 equals 0. Plugging that back, we have x2 equals 0. And going back one step further, we get that, well, at this point, we've sent everything to 0 except for x1, so that has to be x1. X1 is a non-zero thing, so we'll say that the eigenspace is the span of the vector 1, 0, 0, 0. Okay? Because x1 value is actually unrestricted. Okay. Well, how about the next one? So we have lambda equals 5. Well, that gives us a minus lambda I equals minus 4, 2, 3, 4, 0, 0, 6, 7, 0, 0, 8, 9, 0, 0, 0. Oh, sorry, that should be 0, 0, 3, 9, 0, 0, 0, 5. Okay, so again, we're looking for the null space. So in the null space, reading off the last line, we get 5x4 equals 0, means that x4 equals 0. But in the previous equation, that means that x3 equals 0. Okay, and then we're left with, so the second and third equation, because we know x3 and x4 are both 0, those second two equations don't give us anything. And we're left with minus 4x plus, sorry, minus 4x1 plus 2x2 equals 0, since we can ignore the x3 and x4 parts. And that implies that x2 equals twice x1. So this is going to be the span of the vector 1, 2, 0, 0. Okay, so last one we got 1, 0, 0, 0. Now we have 1, 2, 0, 0. Oh, yeah, 1, 2, 0, 0. Okay. Let's do lambda equals 8. We get a minus lambda I is 1, 2, sorry, it should be minus 7, 2, 3, 4, 0, minus 3, 6, 7, 0, 0, 0, 9, 0, 0, 0, 10. Okay, so the last two equations tell us x4 equals 0. And then we get from the previous rows, we have minus 7, 2, 3, and minus 3, 6. Okay, I'm going to ignore x4 because that's already been established as 0. So we can scale this second row by 1/3. This is row 2. So we get minus 7, 2, 3, 0. Let's make it minus 1/3 actually. 0, 1, minus 2. Okay, and then I can add minus 2 times the second row to the first row. R2 plus R1, and I get minus 7, 0, and 7, 0, 1, minus 2. And I'll scale this first row by 1/7 to get, let's make it minus 1/7, why not? So we're left with 1, 0, minus 1, 0, 1, minus 2. And in terms of our equations, that tells us that x1 minus x3 equals 0, and x2 minus 2x3 equals 0, which means that our eigenspace is equal to the span of a vector of the form of a vector. Specifically, I'm going to write it in comma notation. So we'll have x1 is the same as x3, and x2 is twice x3. So we have 1, 2, 1, 0. Okay, that's the eigenspace corresponding to eigenvalue 8. And finally, if we take lambda equals 10, we have a minus lambda I, which is minus 9, 2, 3, 4, 0, minus 5, 6, 7, 0, 0, minus 2, 9, 0, 0, 0, 0. Okay, and now you just have to do standard row reduction to get a system. So these are going to be our pivot variables. And then we'll have one free variable in green. So x4 will determine the values of the others. Let's do that quickly. So we have times this by minus 1 over 9, minus 1 over 5, and minus 1 over 2. I'm going to drop this row, okay, because it doesn't affect the solutions. So we have 1, minus 2 9, minus 2 ninths, minus 1/3, minus 4 ninths. Okay, and then we have 0 and 1, minus 6/5, and minus 7/5, 0, 0, 1, minus 9/2. Okay, and then we can add 2 ninths of the second row to the first row, and 6/5 of the third row to the second row, and we get 1, 0. So 2 ninths times minus 6/5 is minus 12 over 45, and 1/3 is 15 over 45, so it's minus 27 over 45, which we can simplify to give us minus 3 over 5, I believe. Okay, and then in column 4, we get minus 14 over 45, and minus 20 over 45 gives us minus 34 over 45, which does not simplify nicely. And adding in the next, we have this is 0, and then this is minus 9/2 times 6/5 is minus 27 over 5. So this becomes minus 34 over 5. And we get 0, 0, 1 minus 9/2. And finally, we just want to add 3/5 times row 3 to row 1. Okay, and we get, so 3/5 times minus 9/2 is minus 27/10. Yikes. Okay. So the main difficult entry is the top right, which is minus 311 over 90. And the rest of the matrix just looks nice. So we have 1, 0, 0, 0, 1, 0, and we get minus 34 over 5. And in the bottom right, we have 0, 0, 1 minus 9/2. Okay, so if we want a vector in the null space of this matrix, we can take x4, so if we want everything to be integers just to make things a little easier, we can take x4 to be minus 90. Or actually, let's make it positive 90. x4 equals 90, and then this implies that x1 is equal to 311, x2 is equal to 34. Sorry, 34 times 90 is 18 times 5, so we have 34 times 18, which is 612. And then x3 will be, so 90, so we have 9 times 45, which is 405. Okay, so we should have that this eigenspace is the span of 311, 612, 405, and 90. That single vector, which is not the prettiest thing, but when I multiply this matrix by it, I get that it's multiplied by 10. Okay, so now that we've seen a bunch of eigenvalues and eigenspaces, we can consider what the significance of having an eigenvalue 0 means. So we know that if A has eigenvalue 0, then there's a non-zero vector, there's a vector x not equal to 0 such that ax equals 0. But that means that A has a non-trivial null space, which means its nullity is at least 1, which means its rank is less than n. Okay, and in turn it means that A is not a one-to-one it's not a one-to-one matrix transformation, because you have a lot of things mapping to 0, for example. And it also means that A is not invertible. Okay, because think about undoing a matrix transformation which sends a lot of different vectors to 0. Well, then what do you map 0 to if you want to undo this? So there can't be an A inverse. Okay, so that's another criterion for invertibility or versus non-invertibility. So if A has 0 as an eigenvalue, that means it's invertible. And another way to point this out is that if determinant of A minus lambda I, in the case that lambda equals 0, this means this is just the determinant of A, and that's going to be equal to 0. So that means that the determinant is 0, which we know is only for singular matrices. Okay. Now let's take a brief digression to talk about eigenvalues of differentiation. So we know that differentiation from calculus, so differentiation, we can think of it as a map from the space of differentiable functions to itself, to the space of differentiable functions. Okay. And so it's kind of like a matrix operator. Obviously, these are infinite dimensional spaces, so it's not really a matrix, but it's a linear operator. Linear operator because when I take a derivative of a sum of functions, it's equal to the same thing as just taking the derivative separately. And that's one property of linearity. The other one is that if I have a real number times a function, this is the same thing. Taking the derivative of that is the same thing as just taking the derivative of the function and then multiplying by the scalar. Okay, so that means it's linear. So I can treat this linear operator like a matrix and think about what eigenvalues it might have. So are there pairs of, instead of x, I'm going to write f and lambda such that df equals lambda f. Okay, so this is kind of like the eigenvalue problem. It's exactly like the eigenvalue problem, just with f's and d instead of, so this is like ax equals lambda x. Okay, and indeed there are, okay, this is the same thing as saying y prime equals lambda y, or dy dx equals lambda y. And we know, if depending on how much calculus you've taken, you can solve this by taking dy over y equals lambda dx and integrating both sides, which gives us ln y plus c equals lambda x. Actually, let's put that plus c on the other side. ln y equals lambda x plus c. But this gives us, if we take the exponentiation of both sides, y equals e to the lambda x plus c, which is really just ce to the lambda x for a different constant c. So what this tells us is that an eigenvector of d corresponding to lambda is the function f of x equals ce to the lambda x. Okay, and we'll find opportunities to apply these concepts to differential equations a little more later on, but I think that's all for today. Thanks so much.